The James Webb Space Telescope was conducting routine observations of Neptune's atmosphere in November 2024 when it detected something that shouldn't exist. An object, small and faint, moving in a retrograde orbit around the ice giant at a distance that violates every model we have of how Neptune's satellite system formed and evolved. The object measures approximately 12 kilometers in diameter, roughly the size of a small city, orbiting at 1.8 million kilometers from Neptune in the opposite direction to the planet's rotation and all its major moons. This isn't just unusual, it's physically impossible according to our understanding of orbital dynamics in the outer solar system. Objects don't spontaneously appear in retrograde orbits around established planets. They don't survive in stable configurations that contradict the angular momentum of the entire system. Yet there it is, circling Neptune, defying physics, and forcing astronomers to question fundamental assumptions about planetary satellite systems. The discovery happened almost by accident. Webb wasn't looking for moons. The near-infrared camera was mapping methane distribution in Neptune's upper atmosphere, part of a multi-year program to understand seasonal variations on ice giants. During post-processing, an analyst noticed a faint point source that appeared in multiple frames, but wasn't present in any previous Neptune observations from Hubble or Voyager. The object showed proper motion, meaning it was moving relative to background stars, and its trajectory suggested it was gravitationally bound to Neptune rather than a background asteroid or foreground debris. Initial calculations of the orbit revealed the first impossibility. The object moves retrograde, meaning it orbits Neptune in the direction opposite to the planet's rotation. In our solar system, retrograde orbits are rare and always indicative of capture rather than formation in place. Small, irregular moons in the outer solar system often have retrograde orbits because they're captured asteroids or comets, gravitationally snagged by giant planets during close encounters. But this object orbits at 1.8 million kilometers, far closer than any known retrograde moon around Neptune. At that distance, retrograde orbits are unstable over astronomical timescales. Gravitational perturbations from the Sun and Neptune's large moon Triton should have ejected or destroyed such an orbit within a few million years at most. Before we examine each aspect of this discovery that makes it increasingly inexplicable, make sure you're subscribed to Cosmic Outliers and hit that notification bell. We're following this story as new data arrives, and Webb is scheduled for follow-up observations that might reveal even stranger properties. Drop a comment with your theory about what this object could be, because the explanations being proposed are forcing a rethinking of how satellite systems evolve. The object's size was estimated from its brightness and assumptions about surface reflectivity. At 12 kilometers diameter, it's substantial enough to be gravitationally rounded if it has typical asteroid or comet composition. But imaging resolution isn't sufficient to determine its actual shape. It appears as a point source, even to Webb's powerful optics. Spectroscopic observations attempted to characterize surface composition yielded surprising results. The spectrum shows absorption features consistent with water ice, as expected for an object in the outer solar system. But there are additional features that don't match standard ice compositions. Specifically, absorption lines suggesting the presence of ammonia hydrate and possibly methane clathrate, compounds that require specific temperature and pressure conditions to form and remain stable. Ammonia hydrate is found on some outer solar system moons, but its presence usually indicates formation in the outer regions of protoplanetary disks or within icy bodies with sufficient internal pressure. Methane clathrate is even more unusual, typically associated with subsurface environments on larger moons like Triton. Finding both on a small object in an anomalous orbit raises questions about where and how it formed. If this object originated in Neptune's protoplanetary subdisk during planet formation, it should have similar composition to Neptune's regular satellites. They're mostly water ice with smaller amounts of rock and carbon compounds. The detected ammonia hydrate and methane clathrate suggest either formation under different conditions or significant alteration after formation. The orbital parameters deepen the mystery. Beyond being retrograde, the orbit has high eccentricity of approximately 0.4, meaning it's quite elongated. The object swings from a closest approach of about 1.2 million kilometers to Neptune to a maximum distance exceeding 2.4 million kilometers. This eccentric retrograde orbit should be gravitationally unstable. Computer simulations of Neptune's satellite system dynamics show that retrograde orbits at these distances are chaotic on timescales of a few million years. Perturbations from Triton, Neptune's largest moon, which itself has a retrograde orbit but much closer to the planet, should have destabilized this object's orbit long ago. Triton is a crucial piece of the puzzle. Neptune's largest moon orbits retrograde at about 355,000 kilometers from the planet. It's widely believed to be a captured Kuiper belt object, gravitationally snagged by Neptune relatively recently in solar system history, perhaps within the last few billion years. When Triton was captured, its orbit was likely highly eccentric. Over time, tidal interactions with Neptune circularized the orbit while simultaneously destroying most of Neptune's original satellite system through gravitational chaos. The regular moons we see today, small bodies orbiting close to Neptune in the equatorial plane, are thought to be debris that reaccreted after Triton's capture catastrophically disrupted the original moons. If Triton's capture caused such havoc, how did this newly discovered object survive? Simulations of Triton's capture show that the gravitational perturbations should have ejected or destroyed any retrograde bodies orbiting beyond Triton's current location. The fact that this object exists at 1.8 million kilometers, well beyond Triton's orbit, suggests either it was captured after Triton's orbit stabilized, which would require a separate capture event, or it somehow survived the chaos in a dynamically protected zone, which seems physically implausible given the orbital parameters. Researchers proposed several scenarios. Perhaps the object is extremely young, captured within the last few million years through a rare three-body interaction involving Neptune, Triton, and a passing Kuiper belt object. In this scenario, the object would be a recent addition to Neptune's system, explaining why it hasn't been ejected yet. But capture into retrograde orbits at these specific distances requires very precise conditions. The incoming object needs exactly the right velocity and trajectory to be slowed by Neptune's gravity while avoiding collision with Triton or ejection from the system. The probability of such capture is astronomically low. Another possibility involves resonance protection. In orbital mechanics, resonances occur when two bodies have orbital periods that are simple integer ratios. These resonances can stabilize otherwise chaotic orbits by creating gravitational interactions that prevent close approaches. Perhaps this object is locked in a resonance with Triton or one of Neptune's other moons, protecting it from perturbations. Detailed orbital analysis searched for potential resonances, but found none that would provide sufficient stabilization for the observed orbit. The object's orbital period doesn't match any simple ratio with Triton's period or those of the inner regular satellites. A more exotic explanation suggests the object might not be a natural satellite at all. If it's artificial, a spacecraft or probe from another civilization, it could maintain its anomalous orbit through active station keeping, using propulsion to counteract gravitational perturbations. This hypothesis is scientifically valid but requires extraordinary evidence. So far, observations show no signs of propulsive activity, no thermal signatures beyond what solar heating would produce, and no emissions at any wavelength that might indicate power generation or communication systems. The object appears inert by all observational criteria. The possibility of artificial origin can't be completely dismissed without more data. The orbit itself is the primary anomaly. If we can't explain the orbit through natural mechanisms, we're left with either undiscovered physics, unlikely but possible, or non-natural explanations. Science requires considering all possibilities that fit the evidence, even uncomfortable ones. But the burden of proof for artificial origin is high. We need positive evidence of artificiality, not just the absence of natural explanations. Follow-up observations with Webb in December 2024 attempted to detect any changes in the object's orbit or signs of activity. Photometric measurements tracked brightness variations that might indicate rotation or irregular shape. The light curve shows periodic variations with a period of approximately 8.3 hours, suggesting the object is rotating. The amplitude of variations indicates either an elongated shape with aspect ratio around 2:1, or a more spherical shape with varying surface reflectivity. Neither conclusively determines the object's nature, but rotation is expected for a natural body that's experienced collisions or tidal interactions. Thermal observations in the mid-infrared attempted to measure the object's surface temperature and detect any excess heat that might indicate internal activity or recent impacts. The temperature measurements matched predictions for a passively heated object at that distance from the Sun, approximately 50 Kelvin. No thermal anomalies were detected. This argues against recent energetic events and against active internal heat sources. The object appears thermally inert, consistent with a small icy body that's been in the outer solar system for billions of years. Spectroscopic observations searched for emission lines that might indicate outgassing or atmospheric escape. Neptune's magnetosphere and solar wind interactions can sputter gases from satellite surfaces, creating faint exospheres. No emissions were detected from this object. Either it lacks volatile materials on its surface despite spectroscopic evidence of ices, or any outgassing is below detection thresholds. The absence of detectable activity is consistent with either a geologically dead natural object or an inert artificial one. The data don't distinguish between these possibilities. The orbital stability question remains central. If natural, the object should have been ejected or destroyed within a few million years. If it's still present, either it's very young, captured recently, or something is stabilizing it that we don't understand. One team proposed that Neptune's magnetosphere might provide non-gravitational forces that affect small charged objects. If this body has accumulated electric charge from interactions with Neptune's magnetic field and plasma environment, electromagnetic forces could create additional orbital perturbations that happen to stabilize an otherwise unstable orbit. This is highly speculative and would require very specific conditions, but it's not physically impossible. Another hypothesis involves collisional evolution. Perhaps there are many such objects in retrograde orbits around Neptune, and we've only detected one because it's the largest or brightest. If a population of retrograde debris exists, mutual collisions could damp orbital eccentricities and inclinations over time, creating a stable collisional family. Detection surveys would need to be much more sensitive to find smaller members of such a population, but the hypothesis is testable with deeper observations. Researchers also examined whether the object could be a fragment from a larger body that broke apart in Neptune orbit. If a captured object underwent tidal disruption or collision after capture, fragments could be scattered into various orbits. Some fragments might end up in the retrograde orbits we're now detecting. This scenario requires a relatively recent disruption event within the last few million years to explain why the fragments haven't been ejected yet. Searches for additional fragments in similar orbits have so far come up empty, but sensitivity limits mean smaller fragments could exist undetected. The discovery has implications beyond this one object. If retrograde objects can exist at these distances around Neptune, what about the other giant planets? Similar surveys around Uranus, Saturn, and Jupiter might reveal comparable populations. Webb's sensitivity exceeds previous surveys by orders of magnitude. We might be discovering a previously invisible population of small satellites that tell us something new about giant planet satellite systems. Alternatively, if this object proves to be unique to Neptune, that uniqueness itself is significant and demands explanation. The timing of discovery is notable. Webb has been operational for about 2.5 years. In that relatively short time, it's revealed phenomena we never knew existed. This isn't because the phenomena are new, but because our instruments finally have the sensitivity to detect them. The object has presumably been orbiting Neptune for at least thousands of years, possibly millions. We simply couldn't see it until now. This raises the question of what else is out there, invisible to current instruments, waiting to be discovered when technology advances further. Public and scientific reaction to the discovery has been measured. Unlike some high-profile announcements, this hasn't generated widespread media coverage. Possibly because Neptune is far from Earth both physically and psychologically. It's not Mars or the Moon, objects the public feels connected to. Neptune is a distant ice giant rarely in the news. But within the planetary science community, the discovery has generated significant interest. Papers are in preparation. Observation time is being requested on multiple facilities. Theorists are running simulations trying to reproduce the orbit through natural mechanisms. The discovery also highlights Webb's capabilities for solar system science. While much of Webb's press coverage focuses on distant galaxies and exoplanet atmospheres, the telescope is equally powerful for studying objects in our own cosmic backyard. Its infrared sensitivity allows detection of cold objects in the outer solar system that are invisible to optical telescopes. Its spectroscopic capabilities reveal surface compositions in detail Hubble couldn't match. And its pointing stability enables tracking of faint-moving objects over time, building up signal-to-noise ratios that expose features previously hidden in noise. What happens next depends on additional observations. Webb's schedule includes further Neptune monitoring over the next year. Each observation will refine the orbital parameters, potentially revealing slow changes that might indicate gravitational interactions we haven't modeled correctly. Ground-based telescopes are attempting confirmation and follow-up, though the object is at the limit of detectability for most facilities. If the orbit proves stable over multiple observation epochs, it strengthens the case that some stabilization mechanism exists that models are missing. If the orbit shows signs of instability, actively changing in ways consistent with impending ejection, it supports the recent capture hypothesis. There's also possibility of discovering additional objects. If Webb's ongoing Neptune observations detect more retrograde satellites at similar distances, it would indicate a population rather than a singular anomaly. A population is easier to explain through natural processes than a single impossible outlier. Collisional cascades, multiple capture events, or dynamical families become more plausible when dealing with groups rather than individuals. A single object demands a single unlikely event. Multiple objects suggest a systematic process we haven't recognized. The name of this object hasn't been officially assigned yet. The International Astronomical Union's naming conventions for planetary satellites require confirmation of orbital elements and physical properties before formal designation. Once confirmed, it will receive a temporary designation in the S-2024N series, indicating a satellite of Neptune discovered in 2024. Eventually, if it proves to be a permanent member of Neptune's system, it would receive a mythological name following the convention that Neptune's moons are named after sea deities and spirits from Greek and Roman mythology. Given its retrograde nature and distant orbit, perhaps something relating to tempests or chaos would be appropriate. Beyond the specifics of this discovery, it represents a broader pattern in astronomy. The universe consistently reveals phenomena that weren't predicted by our models. Not because the models are fundamentally wrong, but because they're incomplete, built on limited data from the small fraction of the universe we've been able to observe in detail. Each new instrument, each advance in sensitivity or resolution, exposes a layer of reality that was always there but invisible to previous technology. Sometimes that new layer fits neatly into existing frameworks. Sometimes it forces revisions to fundamental assumptions. This Neptune object might be either, but we won't know until we understand why it exists where it shouldn't. The philosophical implication is humbling. We study the solar system, our local cosmic environment, with sophisticated instruments and comprehensive theories built over centuries. Yet a small object orbiting Neptune, less than 15 kilometers across, can completely confound us because it exists in a configuration our models say is impossible. If we can be surprised by something in our own planetary system, how much more remains unknown about environments we can barely observe? How many assumptions about planetary formation, satellite dynamics, and solar system evolution are based on incomplete information that future discoveries will overturn? For now, the object continues its impossible orbit, circling Neptune in the wrong direction at the wrong distance, carrying information about processes we don't yet understand. Webb will continue observing, theorists will continue modeling, and gradually, through the accumulation of data and the refinement of ideas, we'll likely arrive at an explanation that seems obvious in retrospect. The question is whether that explanation will be a minor adjustment to existing models or a fundamental revision of how we think satellite systems form and evolve. Either way, this small frozen world has reminded us that even familiar planets in our own solar system can still surprise us. If this investigation into Neptune's impossible satellite captured your imagination, hit that like button and subscribe to Cosmic Outliers for more discoveries that challenge what we think we know about our solar system. Drop a comment with your theory about what's really going on in Neptune orbit, because mysteries like this are how science advances. We find something that shouldn't exist, and in explaining it, we expand the boundaries of the possible.